Hello everyone, class 12 topic is rearrangement of carbocations during dehydration of alcohol at the temperature ranging from 433 Kelvin to 443 Kelvin. We know in this reaction alkene will be the product. Mechanism we have already discussed in previous video in which we found the intermediate was carbocation. Now we know carbocations are able to rearrange itself. If lesser stable carbocation is generated and if there is a possibility to become more stable, it will rearrange itself. Those reactions we are going to discuss in this video. Now let's check what it is. For example, directly with the example we will try to understand. Suppose this is the alcohol whose dehydration we are going to perform. And we know its dehydration will happen in the presence of catalyst, sulfuric acid, temperature 433 Kelvin to 443 Kelvin. We know what is the mechanism. Sulfuric acid will provide us electrophile H positive. That H positive will attack on oxygen because it is looking for electron. Oxygen have a pair of electrons, so it can provide electrons to it. So the next particle that will generate, it will be this one. Oxygen is going to make date bond with this hydrogen, so due to which it will carry a +1 charge. In this condition, it will become unstable, so it will break bond from carbon for the stability. Due to which there is a generation of carbocation. Water molecules will release out. That's why we are calling it dehydration reaction. Now because this carbon has lost its one electron completely, that's why it is carrying a vacant orbital and a +1 charge. We call it 1 degree carbocation. Carbon carrying positive charge directly connected with one carbon, that's why we are calling it 1 degree carbocation. So the final product will be generated according to 1 degree carbocation. But wait, if this carbocation can rearrange itself to better carbocation, it will do it. And this is possible in this case. Look how. This is a carbon which is 1 degree carbocation. The neighboring carbon will shift its hydride. This carbon have a vacant orbital +1 charge. That's why it is able to attract electrons toward itself. That's why the neighboring hydrogen will shift like this. Now this shift is known as 1,2 hydride shift. According to position, first, second, so 1,2 hydride shift is there. Hydrogen is getting these electrons with it, so that's why we are calling it hydride. And these electrons, this pair of electron will make bond with this vacant orbital, a date bond. Next condition generated will be this. This hydrogen will make bond with this carbon and positive charge of carbon will finish because one electron was lost here. Oxygen got its electron, so it has lost its electron, but now it is getting that electron back. This electron, this one, this electron will come here. Out of these two electrons, one electron will be completely toward carbon, one electron will be completely toward hydrogen. So this carbon is getting electrons, so its positive charge will finish, it will become neutral. But problem will be generated for this carbon because it has lost its electron. This electron was of this carbon, so when it will lose its electron, a positive charge will generate on it and vacant orbital will generate on that. Now check, it's a carbocation, it is connected with 3 carbons. What is the degree of this carbocation? 3 degree carbocation. 3-degree carbocation. This we call rearrangement of carbocations. We were expecting final product according to 1-degree carbocation. But wait, if carbocation is able to rearrange itself to better carbocation, it will do it. It can be done by two methods. We call them hydride shift. If you are transferring hydride from neighbor carbon to carbocation, we call it hydride shift. Second is methyl shift. This methyl group can also be shifted toward carbocation to make better carbocation. Here I have preferred hydride shift because after hydride shift I am getting 3-degree carbocation. Suppose I have shifted this methyl group. Please tell me what will be the degree of carbocation generated. If you will shift this methyl group to that side, don't you think 2-degree carbocation will generate? Now reaction will prefer to make 2-degree carbocation or 3-degree carbocation? 3-degree carbocation, because 3-degree carbocation is more stable than 2-degree carbocation. That's why here hydride shift is preferred. So with these two shifts you can convert less stable carbocations to more stable carbocations, and always they will be positioned from 1 to 2. 1 2 it will be 1 to hydride shift, 1 to methyl shift. That's it. This was the main point. Further reaction, you know what will happen. These carbocations will get stability from the neighboring carbon like this, and alkene will generate out here. So that reaction I am not going to perform. Already in previous videos we have understood that reaction. So main point is here that alkene will not generated according to 1-degree carbocation. That was expected alkene, but it will generate in minor amount because 1-degree carbocation is converting itself to 3-degree carbocation. So the major alkene will be generated according to 3-degree carbocations, not from 1-degree carbocation. That's why there will be two type of alkenes, expected and unexpected. Expected alkene will be in minor amount and unexpected alkene will be in major amount. Please try by yourself. Thank you very much. This is the end of the video.